Talking about a new set of stellar population synthesis models that I, in collaboration with Charlie Conroy, Gene Brody, Ben Johnson, and Aaron Ronofsky have made with the intent of better understanding ultra-compact dwarf galaxies. But first, before I get into that, I'll go briefly into some history of why this is a thing we care to do. So, at the turn of the century, we thought, a very clear distinction between the things we call galaxies and the things we called star clusters. And here I'm showing a diagram that you've seen both Gene and Aaron show today, where we have magnitude on the x-axis and log of the radius on the y-axis. And we have, I don't know how to use this pointer. And we have globular clusters down here, and giant ellipticals up here, and a nice big gap between the two. However, subsequent work muddled this dichotomy. First with the discovery of ultra-compact dwarf galaxies, UCDs, then with the realization that compact elliptical galaxies were more common than previously thought. So this, especially with UCDs, as Gene was talking about earlier today, raises the question of what are the origins of UCDs? Do they come from clusters? Are they the high mass end of globular cluster formation? Do they form from mergers of several star clusters? Or do they originate from galaxies, as Gene went into the stripping processes that could possibly form UCDs? Now, there are evidence for both mechanism channels. And as Gene said, we have a few smoking gun pieces of evidence for stripping. The unusually massive supermassive black hole in M60 UCD1, and the discovery of some UCDs within stellar streams. However, absent of such smoking gun evidence, it is difficult to say definitively whether a given UCD originates as a star cluster or originates as a galaxy. And this is something that we would like to know better, because the absence of evidence is not the evidence of absence. So even though we don't see a UCD currently in a stream, doesn't mean it wasn't once in a stream. Just because we can't spend a night each of Keck AO time to look for a supermassive black hole doesn't mean that a UCD doesn't have a supermassive black hole. So we'd like another way to try to distinguish against the different formation mechanisms for UCDs. And what we are trying to do now is use detailed stellar population characteristics as a way to elucidate the origins of UCDs. And by stellar population characteristics, what I mean are abundance patterns, looking at the stellar mass to light ratio, and trying to constrain the low mass IMF of these galaxies, of these objects. So, to do this, what we need are full spectrum models that go out to the near infrared. We need full spectrum models because they're more accurate than equivalent widths. They're now the state of the art. The indices are sensitive to the definition of pseudocontinuum. They're often broadly defined, so you can have more than one element in a given line. And so this is full spectrum model fitting is now what is used in, say, the work of Charlie Conroy and Peter von Dockum. And furthermore, we need to go out to the near infrared because it gives us both independent measures of abundance and it gives us access to surface gravity sensitive lines. And I'm showing several such lines where up here I'm showing lines that are strong in giant stars and weak in dwarf stars, and the vice versa down here. And access to these surface gravity sensitive lines are crucial for being able to constrain the low mass IMF of these objects. And this is something that is key to our understanding of UCDs because many of them have been shown to have elevated dynamical mass to light ratios, but we don't expect dark matter to be around these objects. And we don't expect every UCD to have an unusually massive, supermassive black hole. Charlie Conroy and Peter von Dockum made such models that they successfully applied to early type galaxies. However, The limitation of those models are that they are only valid for solar metallicity objects. And especially for UCDs, we need to be able to go to subsolar metallicities in order to get a comprehensive view of the UCD population. And I illustrate the reason why in this color magnitude diagram from Liu et al. 2015. So this is a color magnitude diagram of objects around M87, where the gray points are the globular clusters, the filled squares are the spectroscopically confirmed UCDs, and the open squares are the candidate UCDs. And as you can see, that many of the UCDs are within the blue part of the color magnitude diagram, which is indicative that they are metal poor objects. So we need to make metal poor stellar population models, and that's what we did. The limitation with the original Conroy and Vandaca models was from the stellar library, which is the IRTF library from Rayner et al. 2009. And you can see in this metallicity distribution that basically all the stars in the stellar library were solar metallicity. So what we did is we made a new stellar library, which I'm showing the metallicity distribution of down here, where we now span a much larger range in metallicity. Then from that library, we made empirical SSPs that depend both on age, and now the novelty of these models is that they depend on metallicity as well. So now that we have these metallicity-dependent SSPs, we can see how this helps us understand metal-poor objects. So I'm showing a couple segments of an LRES spectrum that we obtained for M31B058, which is a metal-poor globular cluster. The gray is the LRES data. The purple line is the best fit spectrum before we included the metallicity-dependent SSPs. Then down here, I'm showing the residual, where the gray band represents the uncertainty given by the error. And you can see that this is just a bad fit. We would not trust any stellar population characteristics that we get from this type of fit. But now that we have the new metallicity-dependent SSPs, which I am showing now the best fit spectrum with the new metallicity-dependent SSPs in red now, we see a much better fit. So especially here, over here around the H beta line, the residuals between the data and the model are now basically within the uncertainties given by the data. So now that we have these new models that give us access to metal-poor objects, we can start to do a comparison between different types of objects and just see what we can figure out and see if we can disentangle the characteristics of the different objects. So here, I'm showing an abundance diagram. So atomic number on the x-axis, abundance with respect to H on the y-axis. So again, I'm showing M31B058 in purple. Now, I also have a solar metallicity globular cluster, which we also have LRES data. This is in magenta, M31B163. And now in red, I'm showing our stellar abundances from M59 UCD3. And also, for the comparison, I have two abundance patterns for early type galaxies plotted as well. One high mass, one low mass. And just with this simple comparison, we can already see interesting differences between the globular clusters and the UCD. So notably, the carbon enhancement of both the globular clusters, which are very different metallicities, are very low, while the UCD's carbon enhancement is higher and within the bounds of this higher mass early type galaxy. But more significantly is the nitrogen difference between the globular clusters and the UCD. Both the globular clusters have very high nitrogen abundance, much higher than either of the early type galaxies. However, the M59 UCD is much lower and again within the bounds of the early type galaxies. And again, I emphasize that the M31 globular clusters are, M31B058 is metal poor, and M31B163 is solar metallicity. So it's not just a metallicity effect that is driving this nitrogen enhancement. So this is our first step in using detailed stellar population characteristics as a way to disentangle the different possible origins of UCDs. But it is just a first step. Now that we have full spectrum models that extend out to the IR and that extend to subsolar metallicities, we want to extend this analysis by first adding more objects, especially metal-poor UCDs. And we're interested in understanding the differences between the stellar mass to light ratios of UCDs and the dynamical stellar mass to light ratios. And again, constraining the low mass IMF of these objects, which we can now do with these new models. And I'd also like to emphasize that these new models aren't just valid for UCDs. They now open up a whole parameter space for all types of metal poor objects. So thank you.
Questions for Alexa? Andre.
It's actually a question for everybody, maybe for Jean, for you. Why can't it be both? Why can't you form ultra-compact dwarfs by combined process, whereby you first form a nucleus by merger of globular clusters, and then that nucleus in a galaxy is left over after the galaxy is stripped? Right, so there could be origin both to globular clusters and to the galaxy.
I don't think we're ruling things out at this point with UCDs, so that could be a valid formation mechanism, but the issue is that until we can look at the detailed characteristics of these objects, that we can't make a prediction one way or another.
Right.
What their origin
I just meant that it could be, in this scenario, you could kind of understand why they both look like UCDs and why it makes sense that they are remnants of galaxies and there is tidal streams around them, right?
Yeah, of course, the ones with the very massive central black hole would be harder to explain that.
Not sure.
Okay, any more questions for Alexa? Oh, it's very nice to... Oh, James got it. Yeah.
I just have a kind of naive question, which is just, think about central star clusters in big galaxies. How different are these ultra-compact dwarfs than just what I would think of as sort of a very dense central star cluster? Are they similar, or...?
So in like imaging, they look very similar, which is why they went unnoticed for so long. People were either assuming that they were just globular clusters or assuming that they were background galaxies and cutting them out of the sample. So that's part of the difficulty in distinguishing one from the other, if there is actually an inherent real difference between them.
I guess they are a lot bigger physically, right? I see.
But
okay.
Yeah, but
yeah. But I'm thinking of these more like central star clusters that people see, and a lot of them have black holes. Yeah, nuclear star clusters. Yeah. Mm-hmm.
So how all these different kinds of compact systems link to each other, relate to each other in the formation sense, I think is a very interesting question.
I think the important thing to keep in mind is that these like size cuts are just, as Jean said, arbitrary. They're just syllogisms, so they don't have any, they don't contain any physical meaning in them.
For globular clusters, so we automatically throw away
we called star clusters. And here I'm showing a diagram that you've seen both Jean and Aaron show today, where we have magnitude on the x-axis and log of the radius on the y-axis. And we have, I don't know how to use this pointer. And we have globular clusters down here, and giant ellipticals up here, and a nice big gap between the two. However, subsequent work muddled this dichotomy. First, say definitively whether a given UCD originates as a star cluster or originates as a galaxy. And this is something that we would like to know better, because the absence of evidence is not the evidence of absence. So even though we don't see a UCD currently in a stream, doesn't mean it wasn't once in a stream. Just because we can't spend a night each of Keck AO time to look for a supermassive black hole doesn't mean that a UCD does galaxies, as Jean went into the stripping processes that could possibly form UCDs. Now, there are evidence for both mechanism channels. And as Jean said, we have a few smoking gun pieces of evidence for stripping. The unusually massive supermassive black hole in M60 UCD1, and the discovery of some UCDs within stellar streams. However, absent of such smoking gun evidence, it is difficult to speak about a new set of stellar population synthesis models that I, in collaboration with Charlie Conroy, Gene Brody, Ben Johnson, and Aaron Ronofsky, have made, with the intent of better understanding ultra-compact dwarf galaxies. But first, before I get into that, I'll go briefly into some history of why this is a thing we care to do. So, at the turn of the century, we thought, a very clear distinction between the things we call galaxies and the things, first with the discovery of ultra-compact dwarf galaxies, UCDs, then with the realization that compact elliptical galaxies were more common than previously thought. So, this, especially with UCDs, as Jean was talking about earlier today, raises the question of what are the origins of UCDs? Do they come from clusters? Are they the high mass end of globular cluster formation? Do they form from mergers of several star clusters? Or do they originate